I would like to hand over as chair now to Alain Dieterlen, who is vice president of the University of Haute-Alsace, vice president for innovation, and we have worked together a lot in UCOR, and he will chair the following session. Thank you very much, please.
Thank you, Johannes, and also congratulations to the organization of this meeting, to see all here together and to work together. We start working in this field with UCOR, but I appreciate that the next speaker will come from Thessaloniki, and as you know, people coming from UCOR are also in another alliances. Its name is Epicure, and Thessaloniki is one member of Epicure, and I hope that we enlarge your connection inside that, into these alliances. And so we will move to the very hot topic, as Johannes said before, we discussed before, and I will give the floor to Dimitri, and I hope we have new conversation after this meeting together, and also directly in the field of UCOR and Epicure, and I give you the floor. Thank you.
So, good morning, and I would like to thank Johannes for inviting me in this conference, in this Science Week. The title of my talk might freak you a little bit more, to take the pass from the previous speaker. So I will talk about the wildfires in Greece and the impact on air quality. And it might be, in a first glance, not very relevant to this session, but it will emphasize that we definitely need innovative energy technologies so that we can have a better future, because the future is now. So what motivated this study? So I will say something about what motivated this study, and Thessaloniki is in an urban environment, so I will first present what is the background in an urban environment, how we measure this with our infrastructure. And on top of that, we have wildfires that even worsen these levels. So, and I will demonstrate this with our measurements. And the concept is that this effect is not local. It might be regional, or even can have global aspects. And of course, the question is this something that happens once every few decades, or it's something that is becoming more and more frequent? So, the motivation, especially for our region, is that Mediterranean, and especially the southeastern Mediterranean, is a crossroad of pollution from different sources. Depending on the level of the atmosphere, we can, oops. Okay, it's not working, okay. So we can have pollution coming from local sources, from Europe, but even also from Asia. So this is something that it's unique for the place. Another peculiarity is that concerning the climate predictions, climate is getting warmer in the Mediterranean 20% faster than in other regions of the world. Extreme weather events are already there, floods and fires, and I will talk about fires today. And say something nicer, that at Thessaloniki we have the good infrastructure that we can monitor these changes, especially for the atmosphere. So some characteristics concerning the background pollution, the urban pollution in Thessaloniki, we are a remote sensing laboratory, so we are not an agency that we monitor pollution on a regular basis to inform the public. So we are more research oriented, and we are active in this field already from the 80s. So I will not go through all this infrastructure, but this infrastructure helps to monitor the changes in atmospheric composition, and there is also a part here that is started in Thessaloniki in 2019 due to the strategic collaboration between KIT and Thessaloniki. This concerns the FTIR measurements. So the infrastructure of Thessaloniki is part of a European infrastructure, the ACTRIS, aerosol clouds and trace gases infrastructure, which is a distributed infrastructure. And Thessaloniki has an ACTRIS LiDAR, which measures aerosol loading and properties of the aerosol in the vertical, and also the state-of-the-art sun photometers, part of the Aeronet, that measure certain properties of the aerosol that are relevant to characterize the aerosol trends, types of aerosol, and so on. So concerning what we have as a regular urban station at Thessaloniki is that aerosol can be affected and characterized by different sources. Most of it's mixtures of different aerosol types, continental aerosols, pollution, but also dust from Sahara and also smoke from biomass burning, wildfires. And you can see here that biomass burning is, the last 20 years, at 10 or 12% of this type of aerosols. And if we have one of the longest time series concerning the sun photometer, the aerosol optical depth, already starting from early 2000. And you can see that we have on the upper panel a time series of almost 20 years showing a negative trend of aerosol, which means that we have some cleaning of the atmosphere concerning practices related to traffic or clean fuels and so on. But you can already spot during the last years that this negative trend seems to level or even have some spikes. And another thing that you can observe is that you see that you have something like seasonal behavior, larger values during summer, and what one can think is that summer is warm period. Warm period means high temperatures and eventually fires, not necessarily wildfires, but I will come back to this. So concerning the LiDAR measurements that allow to measure the aerosol loading also in the vertical, we have, again, almost 20 years of measurements, and this allows us to have some characterization of the aerosol loading in the area concerning different sources like dust, biomass, and continental pollution. And again, here you can see that there are also seasonalities. I will not go very much into the detail. But another issue is that there are certain parameters that can be measured that can also characterize, we call them intensive parameters, that can characterize not the load, but the type of the aerosols. This is, for instance, what we see here as the LiDAR ratio or backscatter exponent, and which means that these parameters are very useful to put them in models because these different aerosols have different radiative impacts and also climate impacts. And this is what we have as a background. So the question is how wildfires, which is something extreme, it's not something necessarily periodical or regular event, affect all these. And we had the bad luck this summer that we have in the area of the southeastern Mediterranean in Greece, 3 very intensive wildfires. The one was very close to Athens, and here you can see the place that it's, this is the Athens area, and this is northwest of Athens, and you can see a very horrible picture there. Another one that was threatened a lot of tourism in Greece was in the island of Rhodes, which lasted for many days. But you can check here the number of the surface that was burnt, and you say, okay, this is large. But if we go to northeastern Greece during August, then we almost had 1 million hectares burnt in a wild national park. And I will focus on this event because this event was pretty close, almost to 200 kilometers from Thessaloniki. So this is a satellite map concerning the aerosol optical depth originating from this wildfire. And you see 2 things here, the extent of a small area, how much affects a much larger area, but there is also another interesting characteristic that you can see in this plot. You can see red means a lot of aerosols, but you can see some gray spots. And these gray spots actually outline that our current algorithms might not be appropriate to be applied to such huge amounts of aerosols, because these eventually are characterized as clouds from the algorithm. But this is not cloud, this is aerosol. So if we now go to Thessaloniki, which is west from that wildfire, you can see how this event was captured from the LiDAR, the upper panel, and from the sun photometer on the lower panel. And you can see during the days how this plume around 4 or 5 kilometers was thicker and thicker. But what is very interesting in this plot is if you see the y-axis. In the first day, we have, in the beginning, in the morning, something like a regular polluted day in Thessaloniki with values close to 0.5 or something like that. And if we go in this day, we have a value of 4, 10 times more, and even a value of 2. This is values that rarely one can observe in a regular urban environment. Even in China, before 10 years or 15 years, you had values around close to 1 or 1.5. So this is something that is not in the wild virgin forests in Central Africa, but this is in Southeastern Mediterranean. And here on the lower panel, you can see also some characteristics of this plume. Again, you have extreme values, but another interesting feature here is that we can identify parameters of these smoke events, because smoke has this peculiarity that changes optical properties as long as it ages. So, and this is very useful to have such amounts of smoke which is pretty fresh compared to what we measure if this smoke comes from much larger distances. And this is something that modelers need to quantify better the impact of such aerosols. And to put it also in perspective, that if we see what is the daily variability of this optical depth, here you can see that the daily value of during August was 5 times more, and all these outliers that you can see were usually fires, but this time the situation was pretty severe. Now, apart from LiDARs that can measure where the smoke is, there are also new algorithms concerning the satellite measurements. Here we have some examples from GOM2 satellite from EUMETSAT, where you can see again the plume concerning what we call aerosol index, where it shows where the aerosol is. But on the lower panel, you can see also at what height this aerosol is. And this is, although I would say this is the scientists sometimes feel like if they have conditions like that to test algorithms and to validate algorithms. But again, this might be useful also for future studies. And this is the same pattern and the same scene observed with a much higher resolution satellite like Tropomi, which has a very small footprint, and you can see many details. So again, you can see how this plume evolved and at which height around the whole southeastern Mediterranean. Now, there are new technologies and new algorithms and new concepts, measuring concepts like the multi-axis differential optical absorption spectroscopy, which developed algorithms that not only measure the total amount of gases or aerosols, but also attempt to make some profiling to see where the gas or where the aerosol is. This is the aerosol profiling during this event, this wildfire event, and you can see how the levels are during the event, and then you can see how it was 1 week before the event. It's amazing that not only it shows where we do or we do not have much aerosol, but also has some indication where this aerosol lies in the vertical, and this is very crucial for the radiative impact. So, but then the question is, okay, there might be aerosols in 2 or 3 or 5 kilometers. Does this affect what we breathe? And according to Copernicus, and this is for August 2023, what are the levels of PM10 at the surface only due to wildfires? And you can see that all these spots in Greece affected also what we breathe at the surface. It's not only the climate, but it's also what we breathe. It's our health, directly our health. Now, besides the aerosols, there are also gases that we monitor and we control their values. And this is the time series of carbon monoxide. And again, I want to stress here that this is a collaboration between KIT and Thessaloniki. We have measurements since 2019. And you can see here the evolution of CO2. And you can see some variability concerning the annual variability that has to do with central heating or traffic and so on. But then you can see some spikes 2021 and some really big spikes 2023. And this is the effect of local fires, the first one close to Thessaloniki, and the other one which is 2 times the regular value coming from northeastern Greece. And this is again from the satellite how CO, carbon monoxide, spread it around the Mediterranean. Now, going to other gases, 2 other gases that are very relevant to air pollution, like nitrogen dioxide and formaldehyde. The first one usually comes from traffic or generally urban pollution, and the other one mostly from biogenic emissions. So here you can see the NO2. The black line is, let's say, something like a climatology, and the red line is what we observed during this event. And you can, if you see the values, they are 3 times more, so it's huge amounts. And considering that NO2 has a short lifetime, this means that there are huge amounts emitted from this biomass burning event. And the same is valid also for formaldehyde, which formaldehyde also comes from, is emitted from trees, actually, during summer, due to sunlight and what trees emit, biogenic VOCs. But then here you have some almost 2 or 3 times more formaldehyde than you usually have during a regular summer in the southeastern Mediterranean. And then again, I will not emphasize this. We have also similar measurements concerning the profiling of NO2 and formaldehyde before and after the event. So, and again, this is what Tropomi captured during NO2. NO2 has a short lifetime, so it cannot reach very easily if we don't have strong winds, larger distances. But then already you can see that during the 22nd of August, this plume reached the poor tourists that were swimming in Chalkidiki. Okay. So then the idea is, it is only something that concerns a fire that happens in northeastern Greece and affects, let's say, 200 kilometers, or this can be even more severe. And there is a very nice example of Canadian fires. Canada is very far from Thessaloniki. But then you can see that smoke from Canada reaches the Mediterranean, and trajectories can reach also the Mediterranean. And if we go to this slide, and you remember the previous one I showed for the wildfires in Thessaloniki, here the axis has a value of 1.1, which is twice the amount of what you regularly have at Thessaloniki. These are the fires in the boreal forest of Canada. And then if we see how we capture and how we measure this at Thessaloniki, you can have a comparison that these are the signature of the fires in Alexandroupoli, which is in northeastern Greece, and this is the signature of the Canadian fires. So although it's 1,000 kilometers away, it gives a very distinct signature compared to local aerosol loading. And you can see how this evolves also in the vertical, that you have a plume coming around 5 to 6 kilometers, which evolves in time, can be thicker, stronger, and can have also, if we go to the right panel, have also very distinct intensive parameters, characteristics that can characterize these aerosols and might be different from the fresh smoke that originate from local fires. And there was a very interesting study, nothing to do with Thessaloniki, but has to do with wildfires and how they impact some global issues, like, for instance, the ozone depletion. And there was a very nice paper from Ansman et al. From Leipzig that demonstrated that the wildfires from Australia or even the wildfires from Canada can be lifted, aerosols can be lifted in the stratosphere, can form polar stratospheric clouds on top of what is usually happening there, and then enhance stratospheric ozone depletion. And this is a new fact. We knew about volcanoes, we knew about heterogeneous chemistry coming from background aerosols, and now we can have a new agent in the play that we have to take into consideration in a climate-changing world. So, coming to the big question, are such events more frequent, or can we say something about that? Can we already say something about that? So, there is some pretty nice system from Copernicus, the European Forest Fire Information System, and here you can have, this is been active since the 2005, I think, or 6. And here you can see time series, the red bars are the burnt area as a percentage of, no, it's in hectares, and the blue line, it's the number of fires. And that doesn't necessarily mean that a large number of fires means a large number of area. It's not always a correlation between that. Maybe you were aware of the 2007 that was in Peloponnese, a very big fire, lasted for many days. But this seemed like an isolated event. Then we had some variability that can be considered the normality in a hot environment like the Mediterranean. And then we see that in 2021 and 2023, we have two really big issues concerning both the number of fires, but especially the burnt area. And we compare this with other countries. Okay, of course you can maybe read the countries, but I can assure you that this is Greece in the middle. And you can see that usually, if you have a large number of fires, you have a big area. This is not the case for Portugal. It's the other way around. So I cannot comment on this very easily, but what is striking is that although in Greece we don't have, let's say, unusually large number of fires, when we have fires, the fires burn a larger area. And this can have different explanations. This can have explanations concerning the climate or concerning the administration, or I don't know. But then, or both. So there is a nice paper from one of my colleagues in Athens that tried to identify some indices. And there are two indices here, that the one called ISI and the other one DCR. And these had to do, the first one considers the moisture in the soil and how this affects the potential rate that the fire spreads. And the other one is another index that has to do how difficult it is to control a fire as the fire grows. So I'm not familiar with exactly how you calculate them, but what we show here, what we can see here, and these are different parts of the Mediterranean, Northwest Mediterranean, and this is the Southwest Mediterranean in the bottom. You can see that although in the Northwest, on the y-axis are the years and the months on the x-axis, you can see that the lower we go, especially in the southeastern Mediterranean, the more red spots you can see. So it might be an indication that there are some trends. This fire spread or the difficulty to extinguish a fire becomes more difficult during the years. And you can see this in different parts of the Mediterranean, northeastern and southwest, southeast. So you can see that in southeast, where Greece is, the last years seems that we have some jump. It's too early to say that we have a trend here, but there are some indications that something changes the last 10 years. So, to sum up and finish with some dystopic pictures. These are pictures taken from my home outside Thessaloniki during this event. These are not clouds. This is the smoke cloud above Thessaloniki. This is in the afternoon. This is early in the morning. And looks like a dystopic scene. But if you see the sun here, and also the lines from the electric network, you can see that it's like a pentagram. Okay, and this is the A note. The A note is the note that the oboe gives to the violin to tune the orchestra. So and I will finish with that. Let's hope that we will still enjoy these beautiful sunrises and we don't let wildfires give the tone. And we will give ourselves the tone. So thank you very much. Vielen Dank für Ihre Aufmerksamkeit.
Thank you. Thank you for this talk and this a lot of data and analysis of the data. So I suppose that you have some question. As yesterday, you can use the microphone in the room. Ask some question. Yeah.
Yes, many thanks for this really excellent insight in this actual situation. I have a very specific question. You mentioned about the PM10 particles distribution. Do you have also any values below that? I'm especially interested in ultrafine particles. KIT is organizing since many years a Brussels symposium on ultrafine particles to health risk. So do you have something about PM 0.1, for example, or anything?
You mean during this event?
During these wildfires?
Not from our measurements, and regular measurements at Thessaloniki are only performed for PM 2.5. So finer particles like that are performed on campaign basis from different institutes at Thessaloniki. I'm not aware that especially in Athens, they might have measured something like that during the fire in Athens. But I don't think at Thessaloniki, no.
Let's talk later. Thank you.
Yeah, thank you for this, also for me, very emotional talk, because it looks like the world is on fire. It's really matching up with the previous talk, yeah?
I told I will freak you out a little bit more, yes.
Yeah, so, but so to also match up, what can we do? I mean, you know, you didn't talk a lot about models, but in a warming world, we will have more fires if we don't take measures. And so are you in discussion with the authorities? You mentioned it very briefly, but I guess there are predictions that the fires will increase if we do not act. So what can be done?
Okay, that's a very good question. The one thing is that we cannot prevent fires from one year to another. What we can try to do is that we try to find tools that at least we limit the spread of the fire with early warning systems or with more innovative technology that spot the fire just at the beginning. Because we can, even if we try to change the climate, this might take some decades to have some impact on the wildfires. So in between, we have to better handle the problem either with modeling or with diagnostic tools and things like that. So I'm not a modeler, so I cannot say much about that, but I can provide measurements to the models that can help them to verify if the forecast or the service they provide is useful or not.
Can I ask another question? And then you stop me if I ask too many. But so, I mean, I think people are very concerned because if these fires occur, and we had it in Germany also as well in recent summers, and this is where people are very sensitive. Usually, you know, people who say, well, climate change is somewhere else or so, but when you have these fires, so do they make the connection already to climate change in Thessaloniki, for example?
I'm not so sure about that. I mean, people are mostly worried about the economic impact of what it happens rather than the climatic or the ecological impact. And if his house is burned or her house is burned, then they might think about the climate. Otherwise, I'm not quite sure. I'm not that optimistic.
Okay, yeah.
Yeah. Yeah.
Right, so maybe I have two questions. In September, so last month, the new planetary boundary paper was out, and now we have the picture. And I was surprised to see that the aerosol category was actually not like passing the planetary boundary. Have you had any expectation that actually we are already passing it? That was one question. The second question regarding what the previous question. I was just thinking, is it possible to spot the places where the fires could occur? And again, we rely now on the infrastructure, that the infrastructure should be there to extinguish it in time. So maybe this could be a solution.
Yes, I know that there are tools that know where to expect a fire. But from that point, to have an effective administration or tools to distinguish the fire at the right time, this might be a very big gap between these two. And this depends also on local authorities or governments and so on. So it's not that easy to answer. Concerning your first question, if I understand correctly, is if we have already on a global scale crossed the limit of the aerosols. I don't think we can have a global answer on that because aerosols have a very spatial inhomogeneity. So for instance, in northern Greece we have big problems with aerosols, in southern Greece we don't. So even within one country, so I cannot give a unique answer on that.
Last question, yeah.
In 1995, we built up the first ever fire observation system in the state of Mato Grosso, which is more or less the size of Germany and France together. And since then, Brazilian states are trying to connect fire with liabilities, with responsibilities. So you can be sued if the fire has occurred on your place and you did not alert this to the authorities. And there is also trials to make fuel management. There are fire ecosystems that are adapted to fire, but there are also many systems that are not. So the tree species, for example, do not have resins that are difficult to incend and so on. So are there any trials to transfer these results into kind of management concepts and legislation to reduce the fire? If you drop a cigarette on the ground, it's actually quite hard to start a fire. So I suppose that most of these fires have actually been set by humans.
Well, it can only happen from the wires from the electrical network. It can happen from farmers that accidentally put some, in their garden, put some fire. The big fire in Athens, in Mati, originated from something like that. There was a trial after that. There was an old guy, 80 years old, and nothing happened. Okay, he was too old. He was just sentenced to 1 year of prison, and then he went out. So I don't think it works this way easily. If you put it put fines or big fines, you have to prevent it. It's too late after that. At least in southeastern Mediterranean.
Thank you. You see that this problematic touch everyone, and we are very close to this question, and we know that also in France and in Spain. So I suppose I thank you again, and we will move to the next speaker, and they have a microphone on the head with Kathrin Menberg for the KIT. Is a junior research group leader here in KIT, so I give you the floor for your presentation. Thank you.
Yeah. Thank you very much. Is it working? Okay. Thanks for the nice introduction. I'm here representing the KIT Junior Research Group on Sustainable Geoenergy and also the chair of Environmental Geology and a group of former and present PhD students who did the work that I will share now. And thanks for having me here. Thanks for giving me the opportunity to talk about chances and risks of ATES systems, which stands for Aquifer Thermal Energy Storage, and it's basically a technology to provide environmental-friendly, sustainable heating and cooling to our buildings, which we all know are a major source of CO2 emissions. So it works the way. Here's a very prominent or famous example from the Arlanda airport in Stockholm. The system had been installed a couple of years ago and has been working pretty well since then. So it's an airport. They obviously have very high heating and also cooling demands. And what they do basically in the winter, they heat their building and they are dropping the waste cold, so to say, into the local groundwater. They are storing it there. And in the next summer, they are basically extracting the cold groundwater, cooling their building with it, and then dropping the waste heat into the groundwater again and doing this every year back and back again, instead of basically emitting their waste heat into the atmosphere and contributing to climate change in that way. And despite the name of the session being Innovative Technologies, the ATIS technology is actually not that young. It has been around for a couple of years. And quite interestingly, the first system was installed in China back in the 1960s. They had the idea of artificially recharging their groundwater with river water, and because the river water was warmer, they decided to reuse this warm climate water to supply their textile industry. And at the peak, actually, they had over 400 systems running in the city of Shanghai. Sadly, they were not maintained in a sustainable way, so they were shut down one after the other. But in the meantime, in the 60s and also 70s, you remember the oil crisis, us looking for different heating and cooling sources. There were some theoretical studies, so all the kind of fundamental work was done about ATIS system, some first ATIS system in Netherlands being installed, some pilot plants in other countries. Those were mostly high temperature systems. So if we talk about ATIS and say high temperatures, we usually speak about temperatures with 50, 60, maybe 70 degrees Celsius. If we say low temperatures, then we typically have a range of like 20, 25 degrees. And that kind of took off the ATIS systems with more studies, more funding programs coming into place, and ATIS kind of distributing, not over the world, but at least within Europe, a couple of systems in the US. So a closer look at this. We had, at the time of the study, around 2,500 systems installed worldwide, most of them in the Netherlands, a couple of more in Sweden, the Nordic countries, and so on. It's a couple of years ago. At the moment, PhD student is updating these numbers, so we're now with like around 3,000, 3,500 systems we have there. If you look at here at the Netherlands, they have all different types of building supplied by this system, so it's mostly public buildings, commercial buildings, but also hospitals and other houses, homes, residential buildings that use this kind of technology. So what's stopping us from taking on this technology in Germany? Also, this has been investigated. If you look at the kind of economic development or growth phases there for specific technology, you have to do a technological development, of course, in the beginning, and then you have this kind of emerging market phase with a few pilot sites and the whole thing taking off. Then you have a growth phase, and you have a maturity phase. And at the moment, the Netherlands are definitely within this maturity phase. A few countries in the kind of growth phase, especially Nordic countries, which have many systems running, people looking at, oh, these systems work quite well, and take this on and distribute it more. Germany here, Canada, US, all in the emerging market phase, and sadly, despite the study being 5 years old, still kind of stuck there, which is, if you look at the problems we're facing, at the beginning, of course, we have to look into the technological feasibility. Is it possible to use this technology and where in the country? We still, especially in Germany, we have a lack of awareness. One thing you can do, of course, is like what I'm doing now, talking about this technology, making people aware of it. And then also, especially in Germany, at the beginning, there's always a mistrust in the technology. So this is something you have to overcome if you want to enter this growth phase. And then, of course, you have different barriers, like what the Netherlands are facing now with more like policy and legislation issues, management issues as well. If you have more systems, it becomes more tricky to manage them. Yeah, so we are stuck in the kind of emerging phase, which is not because there's not a potential. This was a study from Denmark looking globally at the suitability. So it's basically a map that's built upon geological parameters, looking at where is the subsurface suitable for this technology. For ATIS system, we need aquifers, so we need groundwater resources. This is included here. It also includes economic factors, where do we have the economic potential to install these systems. And it also looks into climate parameters, because those aquifer storage systems work best if you have a kind of balanced heating and cooling demand. And you can actually see on this map, of course, in areas where we have dominating cooling demand, like in Africa and South America, it's tricky to store energy because you don't need the heating. The same applies to the Greenland and other high latitude countries, but especially if you look into Central Europe, there's lots of dark green colors in there. Germany is difficult to see in here, which is one reason why a student of us took on this work and looked particularly at the potential in Germany, again accounting for geological parameters, hydrogeological parameters, and also into climate parameters. And you see from a subsurface point of view, more than 50% of the area in Germany that have groundwater are actually technically suitable for installation of these systems. That's particularly the southern German area, Molasse Basin around the cities of in Bavaria. We have the Upper Rhine Valley with Karlsruhe and up to Frankfurt. And of course, we have the northern German basin also with shallow groundwater resources that are usable for this. And a good thing is that the right-hand side map shows the change in this potential for the future, because if we account for climate change, warmer climates in Germany, we will need more cooling in the future. Right now we have a heating-dominated energy system. We will need more cooling, so this will balance the assistance even more, so we have an increase in the potential in very large areas. If you look at ATES systems, again, which are currently installed or have been installed in Germany, these are the locations you can see here. It's dominated by research projects at the moment, which is typical for this kind of emerging market phase. We have a couple of abandoned systems which didn't work out for several reasons, and yeah, also some planned systems at the moment, but still this map is looking very frustrating from this technological point of view, because there's not much going on. And I now want to focus on 4 of those systems which are installed and are either still working or at least have been working for some time. The first one is an ATES system in, I can't point, but in North Brandenburg. That's the red point in the upper right-hand corner. It did work for some time, and then sadly it was stopped, which was not for technological reasons, because I mean they had some issues with the pumping system, which they could solve, but in the end it was stopped because they didn't have a heating source anymore. It was supposed to deliver heat to residential buildings, and if you want to deliver heat in the winter, you need to store heat in summer. This was supposed to come from a combined heat and power plant, but it was too, sort of intermittent over time, and it was just not a geological problem, but just a planning issue from the building side and from the heat source side that led to the end of this one. The second one, it's a bit dark, but I guess you all recognize it. That's the Reichstag building in Berlin. They actually had the first ATES system in Germany a couple of years ago, and sadly, this also stopped. It did work quite well for some time, but then again, a planning mistake from the building side. They significantly overestimated the heating demand and underestimated the cooling demand. So again, the efficiency of the storage didn't work out over the years. It's still working in the sense that they are still using groundwater for cooling, but they are not using the groundwater for heating because they have no heat to re-inject in summer to use it in winter. The third one is our thumbs up example from Germany, from Rostock. That's a residential area, and you might be able to see it. They have solar thermal panels on the roof, so they're harvesting solar thermal energy in summer, super reliant. It's a technology we all know, it's working, storing this heat in the subsurface, in the shallow subsurface, so it's technologically easy to maintain, and reusing this heat in winter to heat their buildings. So this has been in operation for, I think, 20 years. It's working fine, perfect example. They have a kind of advantage because they're in Rostock, which means they're close to the sea, and they're actually allowed to store heat with 50 degrees in the shallow groundwater because it's a salty, it's a saline aquifer, which is not used for drinking water. So they were really lucky to have an authority that allowed them to use this shallow groundwater. But I will come back to this issue in a couple of minutes. The fourth one is the Bonner Bogen, the other green dot here in Germany. It's a kind of hotel commercial center. It was planned, it operated for a couple of years, and then they decided to include a data center in their complex. Data centers have a super, super high cooling demand, no heating demand, and then the same happened as to the Reichstag. Basically, they lost the heat source, they're actually now cooling much more than they're heating. So again, kind of planning operational failure and not a technical failure from this system. And this, the green dot actually the one example, 20 years, high storage temperatures, but then in a saline, salty aquifer. So it's not that easily transferable to other regions, sadly. Ethics systems, as I said, are super sustainable, environmental friendly. This is a study done by one of our PhD students, and he did a life cycle assessment. So he looked into all the things, like processes, materials you need to build those systems, to operate those systems, also to decommissioning those systems, and then compared the CO2 emissions from ATES systems to other German standard heating sources, mainly heating oil, natural gas, or it's a kind of average German district heat value you can see here. And if you look at ATES, what he calculated, those 83 plus minus grams of CO2 will give you an emission saving of 2/3 compared to our standard fossil fuel-based technologies. Pellets and firewoods are performing better at the moment. However, if you consider that an ATES system needs electricity, obviously, to run your pumps and to run your heat pump, the emissions from ATES will get better in the future, which is a very rare case if you compare to all other heat sources. Because if you consider a greener energy mix in 2050, for example, with more solar, more wind, and so on, you will lower the emissions from your ATES system even more, which will give you only 11%, and which then, compared to today, would give you an emission saving of CO2 of an amazing 96%. So one example from Karlsruhe, looking more into the economics, because, like Ander already said, it comes down to the economics in the end in most cases. So we also looked into this. Most of you might know this hospital. It's the city hospital, the Klinikum, Städtisches Klinikum in Karlsruhe. They had a new building, and they were asking themselves, okay, with this massive heating and cooling demand, what we have, what can we do? In the past, they had a groundwater cooling. Then they had the idea, okay, if we can cool, if we can use groundwater for cooling, maybe we can also use groundwater for heating. And we said, perfect. We did some analysis on this one, designed a kind of standard system for them, and then looked into what the economic benefits they would have from installing an ATES system as compared to what they have at the moment with district heating, and the groundwater cooling was shut off, so the standard cooling system would be just a compression chiller, like a big AC, electricity driven on the rooftops. And economics look actually pretty good. So again, including everything from drilling the wells to operating your pumps, and on the same time, all the costs you would have on the other side for the reference system, for your district heating. Also, you would need, if you look into 30 years, you would have maintenance on your compression chillers and so on. So on the y-axis, you can see that the total cost, and you would see that the green line is the ATES system, which in the beginning has higher capital costs. So the installation costs of this ATES system are quite obviously higher because you need to drill. But then the operational costs of this ATES system are quite low, because you have your circulation pump running, you have a heat pump running, but the heat pump is much more efficient than your compression chiller. And also, you don't need to pay for district heating anymore. If you look at the other system, the standard German district heating for heating, compression chilling for cooling, it's lower in the beginning, but actually your maintenance is much higher. And this study, if you look at the date, this was before the Ukraine crisis, so it does not consider the actual increase in electricity prices that we see today. Yeah, payback time would have been 3 years. Sadly, the system was not installed. No, I need to go back. So they, instead of having groundwater cooling and heating, they went for district heating and compression chilling against all economic considerations or numbers that we provided them. Yeah, it's down to one fact that makes me very angry and probably freaks Ander out completely. Because the district heating in Karlsruhe is considered environmentally friendly because it's waste heat from an oil refinery. Yeah, no comments on that. So it's waste heat from a fossil fuel-based technology, but it's environmental friendly because it's there anyways. And then I mean, yeah, the district heating is owned by the city of Karlsruhe. The Klinikum is owned by the city of Karlsruhe. And yeah, heat is basically the cash cow for the city. So they went for district heating and compression chilling. Yeah, we have to deal with the costs now, whatever. If you look only into cooling, you can see that the savings you would have are even bigger. So it is, from an economic point of view and also then from a sustainable point of view, very, very important to also look into cooling and not only into heating. The difficulty with this is that we have a very good idea on our heating demand. That's kind of easy to calculate for residential buildings, but also for office buildings. We have no clue, at least in Germany, about the cooling demand of buildings. So it's really difficult to identify the potential heat sources we can use for our ATES systems, as also the past projects have showed. And one of our PhD students is currently looking into this, and he has a nice workflow of looking onto aerial images, which you can get easily from every place in the world. So you don't need to collaborate with them. You just do like the James Bond spying thing and look down. You identify, oh, these are cooling towers, so these are the typical machines you use for cooling. Either air-cooled condensers, basically large AC units, or cooling towers for bigger purposes. And because they all have this kind of square-shaped thing with a black dot with fans in the middle, they're super easy to see on aerial images, and you can actually then train a neural network to do that job for you. So you feed in the aerial images, like here, that's the aerial image of the Manhattan Financial District, actually. Feed it through your object detection algorithm. It picks out all the AC here, cooling tower there. Then the bigger the cooling tower, the larger its capacity. So you can quantify or estimate the capacity and apply this back into your map. And you can easily look at any map, any place of the world, and see, oh, here's a big waste heat source, here's a big waste heat source, and so on, and feed this information back into urban planning then. This is from Freiburg, so this is an industrial area. Hard to see now with the small dots. But apparently, with the green, all the green lines, there's some big, big waste heat source here in Freiburg, which we could then use to store their waste heat in the subsurface, build a district heating, district cooling network to the next residential area and use this heat for heating in the next winter. One thing that people typically argue and say, oh, yeah, but it's not possible in urban space because there's no space for drilling your holes. And this is the city of Berlin from a project we have there at the moment. And they want to build a Demospeicher, so demonstration ATES, for the headquarters of the Green Party, which is a green building here in the middle. And there is little space. I agree to that. If you just use the courtyards, you can see the three red dots in there. There's not enough space for drilling wells to actually supply enough heating to your, especially because these are old buildings. If you were allowed to use public space, let's say drill a well underneath a pavement area, a sidewalk, for example, which is technically easily possible, you would have enough space to, if you look at the blue dots on the side, you would have easily enough possibilities to drill wells, install a system there, and supply headquarters of the Green Party and other buildings. And another thing is often that people say, oh, but how do I drill those wells in a city center? And even this is possible. Here on the right-hand side, there's a big crane basically lifting the drilling rig over the buildings into the courtyard, and in a couple of weeks it's going to be pushed back. So it is possible. It takes a bit more effort, but easily done. Yeah, coming to the size of the systems, our suggestion is always to think big, because bigger systems are obviously more efficient from a technological point of view, but also more cost efficient. So this is data from, mostly unpublished data from the Netherlands. We have for smaller capacities, our standard geothermal systems, ground source heat pumps, which you see, the bigger you go, the more on the right-hand side, the lower their costs. And if you look at those ATES systems, you can build them bigger, so they're suitable for bigger systems, and you can also see, compared to standard geothermal heat pump systems, they're much more cost efficient. So again, looking at different projects, now for high temperature ATES systems, because people often argue that with 20-25 degrees, we don't get the temperature levels that we need in our older buildings. So there have been many high temperature ATES systems being proposed, but again, if you look at the colors, red colors are abandoned systems. You can see many trials in the past, but not the real success and breakthrough yet. There are some systems under construction, the red ones, and running only the example from Rostock again, and one test site in Wittstock. It's a test site from the University of Kiel. They're just doing some experiments, but I have no intention of converting this into running operating system. If you look at the heat sources, very important, you can see Rostock, solar, that's the one working, Sapporo in Japan also with solar working, and the rest with this artificial cogeneration, those are the red dots. It's always tricky to combine these kind of systems. And then we went to the people who are dealing with those projects and made, at the end, a small risk analysis, interviewing all those experts, ask them then to, based on their experience, so technically, about how would you judge the probability of occurrence of a certain risk, how would you rate the severance of this risk if something happens, and then also what do you think about the uncertainty of this risk. So on the x-axis, you see low risk to high risk. This is basically occurrence and severity, and with the colors, you see the uncertainty of those risks, of those 40-odd experts we had in here. And what you can see is that the technical risks are always perceived lower, and they're also perceived with a very low uncertainty at the moment. The high uncertainties with the yellow to reddish colors, and also the higher risk, more on the right-hand side, are perceived in the financial and especially the political, social, and legal aspects. It's not about the technology, it's about the financial side and the public perception side, especially public perception here in southwest Germany, because incidents like Basel and Staufen are just a Google away, which makes it very tricky, and also shows us that communication with the public is just so important. And also legal aspects, very important, but perceived as a very high risk because there's no constant scheme of subsidies. There are changes in political, also legalizing the permission system, very complicated. One other thing that what's interesting here for us is that if you look at the highlighted, the loss of the heat source, which was basically the reason why half of the German projects failed, is not perceived as a high risk, which is a kind of sort of exclamation mark for us that we need to bring this on the agenda of people, that loss of heat source can be a serious issue, even if you don't think it's like this. Another thing, exploration risk was, first it has a huge range. If you look at the range, it can be perceived super low, but also super high, because this is a site-specific issue. If we look into shallow systems, and we plan shallow systems, with, let's say, the first 100 meters going into the shallow groundwater, they have a low risk of exploration, because for the first 100 meters, we're pretty certain about what's going on in our groundwater. If we look into higher temperature systems, we have to drill deeper, and then we have a higher risk of not finding the site-specific parameters that we would like to have. Yeah, but again, it also shows us in the future, technically it works, we need to put more effort into talking to people from economics, creating business models for the use of those systems, and also talking to the public and making these things possible. So key conclusions, take-home messages. We have a big potential worldwide and also in Germany for those systems. Technically, it can be done. 50% of the area in Germany are usable for this one. For low-temperature systems, yes. For high-temperature systems, there are only 2 worldwide in operation. So there, we need to take a bit care. It will take more to get those systems running than the low-temperature sites. We have major CO2 savings and also cost savings from those systems, so this should not be stopping us in any sense. Cooling is the key, especially the security of the heat source, making sure this is there, and this will also be there for the next 30 years. Because coming back to this issue with Karlsruhe again, with diesel and fuel-based cars running out, we should not be that sure that the oil refinery will be there in 50 years. And we should not rely on this. That's kind of feed source. When planning systems, bigger is better. Just don't do it for your, but do it for your single-family home. That's also good for the environment. But think bigger. Think in like quarter-scale systems or street scale systems. They're much better, much easier. Risks are there, but they are typically not the technical issues, especially not for low temperatures. That's something we can control. They are more on the side of financial and public perception. And then again, for low temperature ATIS, there's very few risks associated with that, and 99% of the worldwide systems are actually on the low temperature side. So that's it from my side. Thanks for listening, and if you're interested in more details, these are the studies we published on this, so there's all the numbers and all the details in there. Thanks again.
Thank you. Is there any question before we make a break? Yeah.
I have one question. Thank you very much for the very interesting talk. Have the KIT considered to install such a system?
Not that I know of, but it might have been in the past. I joined KIT 5 years ago, so it would be a question that I would need to refer to Professor Bloom, because he has been here for long and he might have had some discussions with the KIT before I came here, but yeah. There's a project at the Campus Nord, but they are only storing heat, I think. They're not using it for heating and cooling.
Yes, I can support you with that. We have a lot of various geothermal projects in KIT going forward, and we have to distinguish the various, let me say, levels. We speak about this deep storage project, which is 1,000 meter deep, and we want to store heat there. We have, my question would be, did you consider to combine these way of heat storage with a deep geothermal installation, so you have a constant heat during summertime, which you can store into the ground? That would be an option which is CO2 neutral. Just a last remark, I was a bit disappointed to hear from you that we only have a few projects in operation. I always try to, let me say, to make advertisement for these technologies, and I was pretty much optimistic that we have much more systems running in Germany. So you brought me back to the realistic situation. Thank you.
I mean, one thing I have to say about the research projects, 2 years ago there has been a call from the BMBF on thermal energy storage, and this map was from 4 years ago. So we are currently updating this map with projects, but they are research projects. They often have a demonstration side, but if you look at the really commercially running systems, there are not many. That's true. And yes, you could secure a heat source if you go for like storing the heat in a deep subsurface and using a cold storage in the upper side. That's true, but again, then you are on this high risk side, especially for your exploration. And in my perspective, to make people aware of this issue, we need successful demonstration projects. So we need to lower the risk. We need to go for the low-hanging fruit, build a shallow system for low-temperature buildings. Then we cannot supply those old buildings that need supply temperatures up front of 60, 70 degrees, but we can supply new buildings like this one, for example, that have low exergy heating systems. Then it's possible to go for this low-hanging fruit, low-temperature, shallow systems where we have no technical or much less technical risk than if we go for the deep one. The deep ones are fine. I think they should come as a second step. Once we show, hey, low temperature shallow is working, we can also tackle this public awareness and public perception thing, show people we can deal with it in the shallow subsurface, and now we can go deeper. but one step after the other, crawl before you walk and run.
Thank you again, and I think that we have a break for a half hour. Okay, thank you again. And,